Good evening, and welcome back to Vegas October 1 Sounds. Tonight's going to be a little bit more of a technical discussion, and I'm going to talk again about the Vera system that was developed by a few students at the Carnegie Mellon University. And this has been in the news, I don't know, for the past year, I guess. At least I've followed them for more than 18 months. And what they've done is provide an online system where you can upload some videos, and from those videos you can align them, much like what been doing in the past few videos with the marquee sign out in front of Mandalay Bay. And then from that alignment, you can make projections on the shooter location using some concepts and definitions from hyperbolic curves, which I'm not going to get into tonight. And also there's a second part of their system where you can make some estimations of the shooter location based upon a single video and the lag, i.e. the difference in time of arrival between the muzzle blast and the shock wave, and a few assumptions. And I'd like to talk about this method 1, which is the lag part. And what I really hope to impart tonight is a better understanding of how to use their system and know its limitations and the nature of the question that you're really answering. So what I did was I took their source and perused their source code and extracted out the essential algorithm for Method 1. And then I played around with it a bit. Now fortunately it was written in Python, and I'm fluent in Python. And so what I have is a set of routines here, at the core of which is an algorithm that uses linear algebra to solve some equations. And for everybody watching, yes, this is Greek, and this is unintelligible unless you first know the theory behind gunshot acoustics. And to do that, we have to take what they're proposing. But in the end, this algorithm, the core part of it, comes up with an answer for two unknown variables called T1 and T2. And I'll show you here momentarily what that means. If you want to peruse this after you've watched this video and go to the technical report, you can download it by clicking there. And right now we're at https://vera.cs.cmu.edu, and you can go to that website and look here. But if you click on that technical report, you'll come up with a place where you can download the PDF over here on the upper right hand corner. And when you do, you'll get this. This is their explanation of what they do. Now for me, I'm going to go right to the PDF because I have it already available to me and I can do different things with it. So let's start talking about Method 1. So Method 1 is you take a single video, you extract out the lag. Well, just as a refresher course, let's do that. So first what I do is I have to pick a location. So let's go to Google Maps, or shooting maps, excuse me. And in this case I've picked this video, which is release batch 13 number 120, and it's located down near the corner, which you can see right here. It's not quite as far north as the guy on top of the bathrooms, and it's not quite as far south as Mandalay Bay Road. So it's a little bit in between, but it is on the west side of the venue, close to the Vegas Boulevard. And since most of my videos, so I'm going to choose that one. And here you can see, thanks to the shooting archive and this shooting map, there is a whole lineup of approximately in real time when these volleys occurred, and then over here on the right the time in the video at which they occurred. And I'm going to look at volley 9. So I would download that and then go to volley 9, which should be about 5 minutes in, and I use the tool called Sonic Visualizer, as many of you may be aware, and I've loaded it up. And so in this case what I've got is volley 9, and it consists of 3 parts. You got a short little burst up front, followed by a long burst, and then a third part. And so it's 3 parts. And most recently I've been talking about the second burst, the first shot. And so that's where I'm going to measure the lag, just simply because I've been talking about it. So if I take a look here and I expand things out, then what I can do is on this second pane here, this one right in the middle, which is a frequency versus time plot on a logarithmic scale for frequency, so I see a lot about the lower frequencies. And got to get this out of the way this time. And I've adjusted the gain so that I can see right about when the muzzle blast first occurs, which the first muzzle blast is in this region right there, and the first supersonic crack is over there. So we can see that there's quite a bit of a distance between the two. In this case I've measured it out, which if you go up here to Sonic Visualizer, click on the select and then just drag there, let's just do that. Normally we'd be here, so I'd click on the select tool and I'd start there, press the left click, go down, drag over to the muzzle blast, and then read the time as 0.3649, or just call it 0.365, and that's how I measure the lag. So I take that number, 0.365, and then I go over here into my system where I have extracted the essential algorithm and drop down to where I actually run through it a little bit and plug in this case I got 0.367, so let's change it to 0.365. Now that's not enough information to run the Vera system, and it's not enough information to run the essential core algorithm. In fact, what I've discovered is that the essential core algorithm accepts several different parameters. And just going back up here to the definition, we get a range for the lag, a range for the thing called alpha, which is an angle, a range for the bullet speed, and a range for the speed of sound. So we can change all those parameters by giving them either a single value or a range. Now in this case I've chosen a single value for the lag, 0.365, but I could have given it a range. And I said that the alpha angle is 10 degrees. Now to understand what the alpha angle is, you have to go back over here to the pictures, drop down to page 3, I think. Was this page 3? Yeah, page 3. And in this diagram you'll see right here that the alpha angle is the angle measured in a clockwise direction from the trajectory of the bullet to the line that intercepts from the gun to the recording. So the gun is located at point A, the recorder is located at M, the bullet flies in the direction from A to B, and the angle between them measured in a clockwise direction is alpha. So that's the shooting angle. So now we got to know something about that. Theta, which we'll talk about in a minute, is the Mach angle, and that's simply the speed of the bullet divided by the speed of sound. So let's see what other parameters the program is looking for. We're dealing with. So that's what that is. Now in this case, I've put in 10 degrees. What does that mean? Well, if we go back over here to the shooting map, or even let's go to Google Maps. First off, we got to remember where this. Well, let's just shrink things down here. If I to know alpha, you have to know something about the shooter's location, right? Well, that seems counterintuitive to me, because the whole question is, where is the shooter? How far away is the shooter? And so it's kind of you got to kind of know the part of the answer before you can get the answer. And that's one of the pitfalls of Method 1 from the Vera system. But if we start making assumptions, we can narrow things down. So if we assume that the bullet was fired from Mandalay Bay and went northwest across the venue, then we can sort of say, let's get a little bit cleaner picture here. And here I'm going to use my lag map. So if we were to draw on this in Let's go pink, yeah. Then with Mandalay Baby, and over here, and we were to draw northwest like that. Okay. Then we'd have to ask, where is the that video located? And it's located right in here. Not a very good color, is it? Okay. So in that case, the angle between where the shooter is and that is, pretty small. We'll say 3, 4, 5 degrees maximum. But now this all assumes that we know the path of the bullet. We may not know the path of the bullet. The path of the bullet may actually be something over here, and the angle would become more like 20 degrees. So you see, we have to do a sort of a trial and error run on this thing. So I'm going to say that the average path of all bullets was this first thing here. And I'm going to say that this initial guess of mine is, let's say 3 or 4 degrees. Say 4 degrees to begin with. All right. So this is what you'd have to do in Vera. They have a nice web interface. So let's drop back over to my program here and type in, let's go 4 degrees right there. And I could give it a range, but I just want to start out simple. So one value, 4 degrees. Then we have a number for the, got to erase some of that stuff so I can see my program here. All right. Then we need 2 other parameters, which is called the range for the speed of the bullet and the range for the speed of the sound. So once again, we're left with a dilemma. Well, how do we know these things? So got to make some guesses. And when we do, we can run the numbers and see if our guesses ended up with an answer, namely the distance that makes sense. So this isn't like it absolutely predicts the distance knowing just the lag. No, you have to know the lag of the approximate angle between the bullet path and your recording location, the approximate range for the speed of the bullet, and the approximate range for the speed of sound. Now the speed of sound is not too bad because we know the temperature roughly that night, and from that we can calculate out that the speed of sound was somewhere near 1150 feet per second. So that one's not too bad. So when I go down to here, this program part where I plug in the values, I just put 1155 to 1155. So now comes the speed of the bullet. Here again we have to make an assumption or a guess, and I'm going to say that for a close distance to the shooter and for a .223 round with a 55 grains bullet attached to a 223 cartridge that would be fired from an AR-15, I'm going to say that the initial velocity is 3,200 feet per second. And that's a guess, and we'll have to go from there, and we can play with it and see what works and maybe hone in on something. And then you can do this over and over and over and repeatedly until you come up with a set of answers that looks the same, and I'll show you how to do that. Now eventually what I'll do is I'll run these simulations, and then I'll plot them on a graph so that you can get a better idea of what's happening. But what I really want to show you here is by changing these numbers, what is the nature of the question you're asking and what is the nature of the answer, because it's not necessarily intuitive. For single values like I'm doing here where everything's just one number, then it is intuitive, and the answer is the distance to the shooter if all those numbers were accurate. But when we start dealing with ranges, we have to be careful. So, and through this little video you're going to come to understand what you have to plug into Vera to get the type of information you're looking for. So let's go ahead and plug this in. We said a lag of 0.365. We think that the bullet missed us by about 4 degrees. We think the bullet was traveling at 3,200 feet per second when the shock wave was generated, and that the speed of sound is approximately 1155 feet per second. So when we plug all that in, and I tell it to go, it's going to print out the minimum, the maximum, the mean, and the standard deviation for this calculation, which I'll get into in another video. So in this case, it calculated, or based upon the information I supplied it, that the distance from our recorder to the shooter in a direct line of sight path is 733 feet minimum, 733 feet maximum, 733 feet mean, and no variance. That's because I use single values. I only used a single value for everything. So you say, well, 733 feet. How does that compare to what we can measure on Google Maps? Let's go up to Google Map, and I brought it up and I plotted from there to somewhere. This isn't precise over here, and it told me that the distance is 824 feet. So you go, well, it missed. It didn't quite predict exactly, so either the shooting location isn't there, or we got the speed of sound wrong, or we got the angle wrong, or we got the speed of the bullet wrong. So let's play with a couple of them and see what might make sense. So the speed of sound, I think, is close enough. The speed of the bullet. Well, if you know anything about the ballistics of bullets, you know that when a 223 high velocity round travels 823 feet, it's lost some speed. But what we don't know yet is where the supersonic crack was generated. It could have been generated close to the Mandalay Bay or close to that. But from all the videos that I've done so far, you know that if you're close to the bullet, the supersonic crack is going to be generated close to the bullet. So that would mean that it would be generated up here near the corner, in which case we need to estimate what the average speed is from here to there. And so I could go to a ballistics chart for that a particular round you chose and grab it and see what it was. I'm not going to do that. I could leave that as an exercise to the reader, but let's say by the time it got there, it dropped to 2,900 feet per second. And then we just run this again. Now remember, we got 733 at the moment. So it increased the distance to the shooter by 50 feet. So that's a closer approximation than the other one. Now the next question is, well, what if we had the temperature wrong and the speed of sound was only 1,055 instead of 1,155? Okay. And then we run that again. And then we see, whoops, wrong direction. So lowering the speed of sound shortens the distance, so we better put it back up. So if we're going to make any error, we should estimate high. Oh, okay, well, what happened if we went 100 feet above it? 1,255. Which I don't think it was 1,255, but just, for running this. In that case, we get, it jumped quite a bit. Quite a bit meaning, 50 to 100 yards, or 100 feet. So, now we've just demonstrated that a small variance, namely 100 feet per second in the speed of sound, can generate a pretty good change in this. So we've got to be careful with the speed of sound guessing. So let's stick it back to, let's make it 1200. Now let's put it back to 1155. I like 1155. Do I really know what it is? Was that? No, because they don't have a precise measurement of temperature, only a guess from the weather station. Okay, so what else? And with those numbers, we run it, and we come up with 782, and our map said 782. That's 40 feet off. So we're 40 feet off. Now, in my book, 40 feet off is a pretty close approximation because all the work I've been doing so far, I haven't narrowed it down to more than within 150 feet. So at this point you would say, well, that little experiment looks like it could be true. So we could say that that's a good result. But it's based upon a lot of assumptions that we haven't necessarily proven now. And so what we would do is take a bunch of locations and do the same process. Because over here, well, let's take one more. Let's take Oasis Apartments, for example. Where is Oasis Apartments? Oasis Apartments is, the shooter was right down here. So let's drag that little puppy down over there and And if the shooter was coming out of the same location, then the distance is now going to be 1,566 feet. Alright, so once again, we're going to assume that the bullet went the same path. Now this time the angle is pretty big. And I'm not real good on guessing that, but I would say it's 50 degrees. So let's plug in 50 degrees. Okay. And if we know anything about shockwave generation, as all my videos have tried to just pound into people's head, we know that for a large angle like that, that the the supersonic shock created by that supersonic bullet is generated close to where the muzzle wave is. So in this particular case, both the shock and the muzzle wave is going to be generated close to where the shooter is. So in that case, we can jump the speed of the bullet back up to 3,200 feet per second and feel comfortable that it's about right. Okay, so what was the lag at Oasis? Well, we got to go measure the lag now at Oasis Apartments. So let's close that down and let's go. I haven't pulled that up yet. So we want the sonic visualizer session for Oasis Apartments. There it is. I'll open it up. So you see, you have to have at least some reliable way of measuring the lag before you can use this. Alright, and here we are at 9B. And in this case, it's a little bit different, but we could still bring up our measuring tool, plop it down there. Oops, got to be up there first. And there's the first muzzle, and there's the first supersonic, and so we have a lag of 0.0362. So let's just say 36 milliseconds. So we're only going to 3 digits here. 36 milliseconds. So we pop back over to our program and type in 0.036. Alright. And then we say, give me the answer, baby. Well, that didn't do us any good, did it? It says that the distance is 775 feet. So that doesn't agree with anything at all. So what's wrong here? Well, the only thing that we don't have pretty good estimate on is this degrees. So maybe it was more like 60 degrees instead of, since for 9B I don't know the precise location of that first bullet. So what happens when you change it to that? Whoa, 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 whoa. I guess 50 degrees was a little closer than I thought. Now it jumps to 3,500 feet. So my 50 degrees was close, but not quite big enough. So what did we just learn? That by varying that angle by 10 degrees, we jump the estimate of the range from 700 to nearly 3,500. So as you can see, this is even more sensitive to that than it is to the speed of sound changes. And the reason is because at that large angle, the numbers become really, really small for the lag, and a small change in the lag can generate a large change in distance, essentially. So let's say 55 degrees. We'll hone in on one here. And what was our actual number? Google Maps was 1566. 1566, and we got 1431. So maybe it was 56 degrees. Yeah, close enough. So in this case, guessing that the miss angle is 56 degrees or 55, that we measured the lag, we can pretty much say that the bullet was at its maximum speed close to the window, and that the speed sound is that. We're going to get a distance of 1622 versus what we can measure of 1566. So, we're off, tens. Let's see, 1566 minus 1566, 15, yeah, 100 feet. So you can see how a small error in either measuring the lag or measuring the angle at large distances, at large angles from the path of the bullet can have radical implications for your estimate of the distance to the shooter. So, in using Vera, you have to understand that this angle they call alpha here is not the angle of the bullet, but the angle between the bullet and your shooting location, which isn't explicitly clear in their documentation, and you have to read very, very carefully to understand it. When I first ran across that, that was quite a big surprise for me. Okay, so now we have a basic understanding of how to use Vera for the method 1. We have a conceptual situation where our proposed solution of Mandalay Bay agrees with that, but that doesn't necessarily mean it's the only solution, because if we go back to the technical report and you see what the result of their thing is here, they have a range. So they plugged in ranges and they came up with these concentric circles identifying the potential shooting locations, and it's all over the map. Okay, because a single distance doesn't identify which side of all these curves you're on. It only identifies a distance. And so you have to use some judicial choices. But so is there another solution which will meet this criteria? Well, without knowing which direction the bullet came from, we could actually say that the mirror of this, which is that the bullet was coming from a location that was the same distance away from Mandalay Bay but in the opposite direction, would probably also qualify. Right? You get that? So you have to have some other means of qualifying which direction the bullet is coming from, because both those solutions would be good. Solutions up here aren't going to be quite as good because they have other implications. So you have to run multiple of these things, and by the time you've run 3, 4, or 5 of them, then that volume of information pretty much precludes or limits the solution to being one particular area, just like in the last video where I did boxing and the shooter. After about 3 different numbers, you have a pretty good idea of where it's at. So this is just another way of calculating the distance to the shooter using the Vera stuff, but you have to remember that you're making a lot of assumptions and a lot of guesses. So it's more like as I call it, a forward-looking experiment. And the forward-looking experiment is, if I were at the Mandalay Bay and my bullet was traveling at 3,200 feet per second right outside the window, and it was a .223 round with a 55 grain slug, and the temperature was this, and the bullet went in a certain direction, then and I measured the lag, then the distance, does it agree with all that? So it's sort of like a what-if scenario. Whereas the boxing solution that I presented last night doesn't need any of that. The only thing it needs is 3, 4, or 5 different locations working backwards, and from that all you need to know is the time of arrival, and all you need to do that is to sync up the videos by some means. And Vera can actually use that approach. It doesn't use the boxing algorithm, but it uses the parabolic algorithm, which is more accurate than the boxing algorithm, and essentially works on the same principle, that by overlapping the results from hyperbolic curves, you can narrow down the shooting location. Alright, so that's the basis of the method 1 of Vera. So now let's go in and tinker with the ranges and think about the questions that we're asking. So we've had 2 or 3 examples here. Now, what if I had said, rather than a single number, what if I had said 53 degrees to 55 degrees? So I plugged in a range now for the shooting angle. And when I run that, what I'll get is something a little different. Okay, so in this case I got a minimum, a maximum, an average, and a standard deviation, because changing this range allows for different numbers, just as I demonstrated that by changing it just 5 degrees, or 10 degrees rather, it changed it by 20-some hundred feet. So for a range of the shooting angle between the bullet and Oasis Apartments ranging from 53 to 55, we can get a estimated distance to the shooter varying from 1,094 to 1,432 feet. And that's all assuming a constant velocity of 3,200 feet per second and a constant velocity for sound of 1155. So when you start changing these things into range, then this distance of 400 feet, let's say here, is quite a difference. And you'll end up then with this type of thing where essentially it covers the minimum distance and the maximum distance, and that covers a vast portion of the whole shooting area last night, which you have to do multiple of these and overlap them and see, just like on the boxing algorithm, which area is the hottest or the most limited. So for the Vera system, when you do multiple of these plots and you overlay them, it's an additive thing. With the greater the addition of the red zones, you'll come up with a super red zone, and that's the more probable of the shooting locations. Alright, so what about if we change other parameters? Rather than changing that angle so much, let's put it back to 55, just 55. And whenever I make a change, I rerun it to make sure I'm close. So it must have been 56 we were using, because that's not close enough. Yeah, that's close enough. So let's ask the question, what if we miscalculated the lag by 3 milliseconds, or 3 out of 36, which would be 10%. Now remember, 1662 is the answer currently. And then we run this again. So we went from 1662 to 1523, which would be 140 feet for a 3 millisecond change. It's not hard to make a 3 millisecond error in the measurement of your lag. So for every millisecond, we're jumping 50 feet. And that's again why when I say it's southwest of the venue at an elevated position, located within a sphere of a diameter of 200 feet, I say it because if I had made a 3 millisecond error in my measurement of the lag, then I would have a 150 foot change in my estimated distance. And that's assuming all the other variables remain constant. So here you can see that sometimes a small change in one single parameter can yield massively different results, and so they become really, really critical. And it's those long distances at large angles that can really skew your results. Alright, so now what if we were to say that the bullet speed, we're going to keep everything constant here. Let's again run it, make sure I'm at the correct answer. I was like 1662. Okay, what if the bullet ranged in speed from a low of 1600, which would be out quite a ways, at which it drops down to 1600 feet per second, to that, and we ran this little puppy again, then we would get ranging everything in the range of 1662 to 2143 with a standard deviation that I can't read or make any sense of. Wait a minute now. Why do these second numbers here just not even make any sense? I mean, that doesn't even make any sense. I don't know. Well, must have reached. Let's bump this up to 2600 then. Must have reached a corner case where it makes no sense whatsoever, and they do exist. Yeah. So we exceeded the limits of what the algorithm can calculate. In that case, much like what they do in their code down here, they say that if any of the distances calculated is less than the elevation, which in this case would be 0 or 300 rather, then and if the elevation is greater than 0, then we set the values to the minimum of the distances or the elevation by a different algorithm up here. So they've taken care of that in their stuff. I haven't added that into my code as a error condition. So let's get back down to calculating. So there are situations, even in the Vera system, where making too big a change is going to generate an error. But for this case, where we said the bullet velocity varies between 2600 and 3200 feet per second, then you're going to get this calculated range that would vary between 1662 and 4700, which is just all over the map. You couldn't tell anything from that at all. I mean, 3,000 foot variance? I don't think so. Or 3,000 foot minimum to maximum. And here they say that the average of all those things would be 2,600 and something, with a standard deviation of 824 feet, which would be completely unacceptable for trying to find the shooter. So now, what does this variance in bullet speed mean? Does it mean that you're saying that the bullet at the muzzle exit can vary between 2600 and 3200? Or does it say that the bullet along its path will vary between 2600 and 3200? And if so, what does that mean? Well, to answer that question, you have to understand the nature of what is being calculated and apply it accordingly. In this case, I'm saying that if I have a fixed miss angle, I've got a very specific lag and a very specific speed of sound, then what I'm doing is, and in this case, regardless of what the speed of the bullet is, that both the shock wave and the muzzle blast are created at very close to the muzzle of the gun, then this is an experiment that says what happens when the bullet slows down. But you could rewrite it the other way, and the same exact numbers here, you could interpret it a different way. If, rather than missing a 56 degree, let's say that was 5 degrees, 5 degree miss, and we measured a lag of 36, and the bullet varied by 26 to 3200, and we ran that. So then we would get a distance to the shooter of 74 to 86, in which case it would make sense that we are asking multiple types of bullets. That is, what if we had a bullet that when it exited the muzzle at 2600 feet, or 32, or all the way between that to 3200 feet per second? How much would it change the estimate of the distance to the shooter? Which, because we're right on the bullet trajectory, then the lags grow pretty much linearly with the distance away from the shooter, or the downrange distance, and so the small lag would mean a small estimate of the distance to the shooter. Now in this case, once again, this isn't a realistic number that doesn't account for elevation, because in this case the distance to the shooter is smaller than the elevation of the shooter, and you have to add that back in, which but there's a way in Vera to account for that also, or they just say you can calculate it yourself, which there's an algorithm up here that I have not integrated into this little programming experiment. So you could use this parameter in multiple different ways, and you could use any of these parameters in multiple different ways, but they have to be applicable to the real physics of it. You can't just plug and chug and say, oh yeah, that's that, because it won't hold up under the physics. You have to have realistically estimates of those things that work in the physics. That is, in this case, where I'm saying for a 5 degree miss, that would be potentially realistic, but for a 56-degree miss, that bullet speed makes no sense whatsoever, because all the sounds, both the muzzle blast and the shockwave, are being generated almost right at the gun. So the bullet's not going to vary by that much. And similarly, you have to take that into consideration for each and every lag and know the physics of the thing. So using Vera, just straightforward, there's a lot of, for Method 1 anyway, there's a lot of knowledge requirements on the part of the user, and you should understand the implications of these equations and this geometric model and all the physics associated with it before you go using Method 1. Method 2 is much more simple, and Method 2 is the one which I'm not going to talk about tonight, is where you take a couple of videos, you align them, and then you measure the sound, the aligned sound or the unaligned sound, whichever way you want to look at it, and it comes up with this parabolic curve, and then you take a different set and it comes up with a different parabolic curve, and where the parabolic curves interact. Let's see, do they have a picture of that? Somewhere they did. Yeah, up here. See, there's multiple parabolic curves there because you measured 3 points, 3 videos, and you took pairs of them. There's 2 pairs, and the overlapping of them indicates the most probable shooting location. In that case, you don't have to know much about the gunshot model whatsoever. All you have to do is plug in a couple of numbers. So I would suggest that people wanting to use Vera without a great understanding of gunshot acoustics, stick to the parabolic or Method 2 and shy away from Method 1. For those who want to use a single video with a single measurement of lag and they want to plug and chug into Vera, you better know quite a bit about the nature of gunshot acoustics. And by quite a bit, I mean a deep understanding, because the numbers won't make sense otherwise, and the values that you plug in aren't going to be realistic and make sense. Okay, so that's pretty much what I wanted to talk about Vera. Method 1 is, it's not just a simple thing, and you're doing more estimating than you are finding exact numbers, and those estimations can have a huge impact on the numbers that pop out. So take everything with a grain of salt, take lots of measurements, do lots of trials, find some overlapping circles on them, and be wary that if you're using that Method 1, that you can be subject to quite a bit of questioning, as you should be. But I have demonstrated using some reasonable numbers that the Vera method will come up with a pretty accurate distance model if your estimates are accurate. All right. Let me see if there was anything else I wanted to talk about. No, the technical document, no. The program, no. I'll do one video strictly on what all these equations mean and why they're written that way for the very technical inclined, but I'll do that a little bit later. The next one I want to do a couple, 3, 4, 5 days down the road is on the parabolic method. And once again, I'll find the code in their system that does the calculations and grab it out, pull it over into my little cache, shall we say, of algorithms, and run a few simulations on it and see what it really means and what parameters you have to provide for it to make a reasonable calculation. All right, so that's it for this evening, and we'll catch you in the next one, and have a good evening.